There's little doubt that humanity stands to learn something genuinely new from the interstellar object 3I/Atlas, regardless of whether its nature ultimately proves to be a conventional icy body or something far more unconventional. The true barrier to learning is not the object itself, nor the limits of our instrumentation, but rather a cultural and intellectual resistance rooted in what might be called the arrogance of expertise. This resistance manifests when self-identified experts assert unwarranted certainty in domains where empirical knowledge is sparse, and where novelty should instead demand humility and curiosity. It is difficult to understand how anyone can credibly claim expertise on interstellar objects when, prior to 3I/Atlas, only two such objects, 1I/Oumuamua and 2I/Borisov, had ever been observed. A sample size of two hardly constitutes a robust empirical foundation, particularly when the third object displays a large number of anomalies relative to the first two. In any other scientific field, such anomalies would be regarded as invitations to explore new physics or new interpretations, not as inconveniences to be explained away within pre-existing frameworks. One of the most striking and under-discussed features of 3I/Atlas is its anti-tail, which appears clearly in the highest resolution images obtained by the Hubble Space Telescope, both before and after perihelion. The behavior of this anti-tail is particularly puzzling because its orientation flipped relative to the object's direction of motion at perihelion. This is not a simple matter of projection effects or observational perspective, as is sometimes invoked for ordinary comets. The geometry and timing of the flip indicate a genuine physical phenomenon that demands explanation. In classical cometary physics, tails form because dust and gas are pushed away from the nucleus by solar radiation pressure and the solar wind. These forces act in well-understood ways on micrometer-scale dust grains, producing tails that point approximately away from the sun. An anti-tail, by contrast, points toward the sun or along unexpected directions. And in the case of 3I/Atlas, its persistence and flipping behavior make conventional explanations inadequate. If the anti-tail were composed of micrometer-scale, refractory dust particles, these particles would have been rapidly swept away by solar radiation pressure and the solar wind. They could not plausibly maintain the observed structure or orientation. This strongly suggests that the anti-tail is composed of something else entirely. In response to this puzzle, I have written 3 papers exploring alternative physical explanations. One possibility is that the anti-tail consists of fragments of ice that evaporate before solar forces can reverse their trajectories. Another is that it is made up of large macroscopic objects, perhaps meter-scale or larger, that are minimally affected by radiation pressure and solar wind. These hypotheses are grounded in physics, testable in principle, and motivated directly by the data. Yet despite this, they have been met with indifference or hostility rather than engagement. This reluctance to seriously investigate the anti-tail of 3I/Atlas is emblematic of a broader issue in contemporary astrophysics, the tendency to force novel phenomena into familiar categories, even when doing so stretches those categories beyond their reasonable limits. Instead of asking what the data might be telling us, some experts insist that interstellar objects must be understood strictly as extensions of asteroids or comets, as we know them from the solar system. Any suggestion that these objects might represent something qualitatively different is dismissed outright, often with ridicule rather than reasoned critique. This attitude is not merely unhelpful, it is antithetical to the spirit of scientific inquiry. To highlight the inconsistency of this response, it is instructive to consider a recent and widely publicized episode from particle physics. 2 major experiments were recently conducted to search for so-called sterile neutrinos, hypothetical particles that do not interact with matter in the same way as the 3 known neutrino flavors. These experiments were motivated by anomalies observed in earlier data, notably from the LSND and Mini-Buoni experiments, which appeared inconsistent with the Standard Model's 3-flavor neutrino framework. Rather than dismissing these anomalies as experimental noise or forcing them into the existing model, physicists took them seriously enough to propose a new particle and design large, expensive experiments to test that idea. The micro-Bueni experiment used oscillation data from 2 neutrino beams to test whether a single sterile neutrino could explain the earlier anomalies. Its results excluded that interpretation at the 95% confidence level. The Cochrane experiment, which examined the beta decay spectrum of tritium with extraordinary precision, searched for distortions that would signal the presence of sterile neutrinos. After analyzing data from 36 million beta decay electrons collected over 259 days, Cochrane excluded most of the parameter space previously suggested for sterile neutrinos. Together, these experiments cost roughly $90 million. Yet no one seriously argued that this effort was a waste or that the sterile neutrino hypothesis was nonsense on stilts. On the contrary, the experiments were widely praised as exemplars of how science should respond to anomalies by testing bold ideas with rigorous methods. This contrast raises a profound question. Why are anomalies in particle physics treated as legitimate motivations for speculative hypotheses and costly experiments, while anomalies in interstellar objects are dismissed when they suggest possibilities that extend beyond conventional astrophysical categories? The idea of a sterile neutrino introduces an entirely new particle, fundamentally altering our understanding of the universe at the most basic level. Yet this idea was treated with respect and seriousness. By comparison, the suggestion that some interstellar objects might have a technological origin, an idea that does not violate known physical laws but merely extends them into an unfamiliar context, is treated as taboo. The resistance becomes even more striking when considering the editorial and institutional pressures applied to suppress certain lines of thought. In my own work on 3I/Atlas, I noted that if the object is a solid body with a physical radius larger than 10 kilometers, then the limited reservoir of rocky material in interstellar space would imply that its trajectory toward the inner solar system may not be random, but instead favored or even designed. This statement was not presented as a conclusion, but as a conditional inference based on reasonable assumptions. Nevertheless, the editor of the journal to which the paper was submitted insisted that this sentence be removed as a condition for acceptance. Ironically, this act of censorship motivated the development of a full paper devoted to the technological interpretation, which was subsequently peer-reviewed and accepted by another journal. This episode illustrates that the controversy surrounding technological interpretations of interstellar objects is not rooted in scientific rigor, but in sociological and psychological discomfort. The possibility of alien technology challenges deeply held assumptions about humanity's place in the universe. It blurs the boundary between astrophysics and existential inquiry, forcing us to confront questions that extend beyond equations and models. For some, this discomfort translates into outright dismissal, regardless of the data. Yet science has always advanced by confronting uncomfortable possibilities. The Copernican revolution displaced Earth from the center of the cosmos. The discovery of galaxies revealed that the Milky Way is not unique. The realization that the universe is expanding shattered the notion of a static cosmos. Each of these advances faced resistance precisely because they challenged entrenched worldviews. From a risk management perspective, the refusal to consider technological explanations for interstellar anomalies is particularly puzzling. Even if the probability that an object like 3I/Atlas is technological in origin is small, the potential implications are enormous. The discovery of extraterrestrial technology would have profound consequences for